so we're doing the lymphatic system today. Apologies for the skewed, the skewed view here. I nicked my camera sometime during the recording and I did not notice. Oops. Okay, it starts off a little bit straighter. So we're going to be starting off with the lymphatic system. So the lymphatic system has two main roles. The first role is going to be able to return fluid back to the blood that is left behind in the tissue spaces. In the tissue spaces, it's called interstitial fluid, but once it enters into the lymphatic system, it's actually called lymph. And the idea is to get it back into the blood where it will become part of the blood plasma. While this fluid is being carried through these vessels as part of the lymphatic system, it is also going to be filtered. Now, sometimes you can mix up the role of the kidneys and the role of the lymphatic system because the kidneys are also involved in filtering your blood. However, in the case of lymph, we're filtering really big things like cancerous cells and pathogens and maybe some structures that were left behind in the tissue spaces that you don't want to be left there. And so the kidneys will filter very small things like acids and salts and excess water, but the lymphatic system is in charge of bigger stuff. The first thing we're going to be drawing is a capillary bed, and we're going to draw an arterial end, and then we're going to draw the tiny little true capillaries that are part of that in the vascular shunt. And remember that we go from red to blue. The red colored blood would be on the arterial side, and then it's going to turn to blue colored blood on the venule side. Not a lot of detail here. This isn't really the point of what we're doing. It's drawing a really good detailed capillary bed. Just a quick and dirty one. There it goes. And so in blue, we've got our venule side, and the venules will be leaving out of here. Now, in the capillary beds, remember that capillaries are leaky. This is the area where you're actually going to be exchanging stuff into the tissues. And one of the things that happens here, especially at the arterial end of the capillary, is that you start to push fluids out of the blood. We're not going to be dwelling on the actual numbers. We'll get to some of that stuff down the line when we talk kidney physiology. But it is the general idea that there is some amount of blood pressure still sustained within that capillary, pushing out from the inside, especially in that arterial end where there's still blood pressure. Now, the fluids that are pushed out of there through this hydrostatic pressure are called interstitial fluid. And now they are in the tissue spaces, and they're just present there in the tissue spaces. And in fact, you always have some interstitial fluid. About 3 liters are left behind in the tissue spaces at any given time. You have about 5 liters of blood in your circulatory system, and you have 3 liters of fluid left behind called interstitial fluid, or IF. So it is to this that we start to turn our attention. We think about how we're going to pick up, especially if we have excess fluid left behind, which we'll talk about in a moment. But you can't have this fluid building up, and so you have to have a way of returning it back to the blood supply. So what I'm going to do now is I'm going to draw with a green marker. I'm going to interweave some lymphatic capillaries in green. And so we usually use green to portray the lymphatic system because it sort of runs parallel to the circulatory system. And so here we are running, but we want to differentiate it, of course, with a different color. So lymphatic capillaries are going to have these blind ends, which further differentiates them from the actual circulatory system, because the circulatory system, of course, has no beginning or end. It's just one big circle. Well, the lymphatic capillaries have a blind end, and it is that we are actually drawing right now. We're going to draw some. These are going to be simple squamous epithelial cells that are specialized to overlay each other. It's a really simple little system here. I'm going to be drawing basically 4 cells, and one of them kind of curls around. And so that's the blind end, if you will, of the lymphatic capillary. We're sort of looking at a longitudinal slice, if you will. So what's going to happen is each of these kind of rectangular-ish shaped cells, one end is going to be attached to the surrounding fascia with collagen fibers, which keeps them stable and steady. The other end is going to be loose, and you'll notice that the loose end underlies the anchored end, and so when there is fluid in the region, it can push inward and fluid can enter into that lymphatic capillary. One direction only. It basically flaps the door open. Now I want to draw another aspect of this that we're going to be exploring, which is inflammation. Now here, just a small corner of a circulatory of a little capillary bed that is showing a dilated arterial and leaky capillaries. And you notice everything kind of gets redder and more intense because there's more fluids coming through here, more blood coming through here, and therefore there's actually more pressure extending outward from the inside of the capillaries, and therefore more fluid is left behind. This is, the characteristics of inflammation are redness, heat, and swelling. Redness, heat, and swelling. And so the swelling comes from the idea that you have more interstitial fluid left behind because there's vasodilation, so the arterioles bringing blood in, and then the capillaries themselves are more leaky. So let's draw two different scenarios we're just going to look at two of those underlying lymphatic capillary cells. And we're going to draw that mini valve that exists between them in a normal situation, which is where you have interstitial fluid and proteins entering in, some of the stuff that was left behind by the blood. And then we're going to draw the situation of inflammation. Now, okay, so we have the overlying cell, which has those collagen fibers, and we have the underlying cell, which flaps downward. And what you'll see is in the inflammatory situation, it pushes much harder on that underlying cell, and more stuff is able to get into the lumen of the lymphatic capillary. And let's talk about what that stuff is. So up above, normal situation, interstitial fluid and some proteins will be able to get in there and will eventually be returned to the blood. Under conditions of inflammation, however, you're going to have interstitial fluid and proteins again, but you're also going to have things like excess fluids and pathogens, and even cancerous cells of your body are going to be able to slip in through these mini valves and push their way into the lumen of the blind end of that lymphatic capillary, and they're going to be able to push in and make their way up through the lymphatic capillaries. So we start with what we're looking at here, the mini valves. Either in normal situations or in inflammatory situations, you're always going to have the same pathway. The mini valves open up into the lymphatic capillaries, lymphatic vessels. And then we send the lymph upward into a kind of a collection of the vessels called collecting vessels. And then these in turn will marry together into a larger area called a trunk. Now the trunks drain large areas of the body, like for example the intestinal trunk will drain areas around the intestines, for example. And lastly, there are two ducts that are the final tubes that allow this lymph to be pushed directly into the blood supply. So there are two ducts. There's the thoracic duct and there's the right lymphatic duct. And the right lymphatic duct will empty into the right side of the body and will drain sort of like the right arm, the right side of the head, whereas the thoracic duct will drain pretty much everything else. Now the way that these ducts work is they do, as we've been saying, eventually empty stuff back into the blood supply. So as long as it's in the lymphatic system, it's called lymph, but the fluid is eventually going to be part of the blood plasma as well. And so what it does is it marries together into this little intersection between the jugular vein, the subclavian vein, and that brachiocephalic vein. They sort of they sort of form like this three-point star, if you will. And so the ducts empty that fluid right back in there. So as it's making its way up, mini valves, lymphatic capillaries, collecting ducts, trunks, and ducts, it's going to be called lymph. The fluid is going to be called lymph. But once it empties back into that blood supply and enters into, the brachiocephalic vein, it is now going to be emptied into the superior vena cava and then back to the heart. So very close to the heart we are here. And at this point, it's no longer going to be called lymph. It's going to be called blood plasma. It becomes part of the blood plasma. There's a few different issues that can arise because of the roles of the lymphatic system not quite doing their job correctly. And so let's talk about two different issues that can arise because of the it's a rather simple idea, the idea of returning lymph eventually to the blood. However, there can be things that actually go wrong along this, and it usually has to do with a blockage of those lymphatic vessels, of that entire pathway there. So one of the issues that can arise would be elephantiasis. Elephantiasis is a condition where oftentimes it happens to the feet or to the genitals where they start to enlarge. The feet can start to look very bulky and trunk-like and sort of like an elephant's foot, which I believe is where it gets its name. Elephantiasis is sometimes called by, or I think it's oftentimes caused by filariasis, which is where parasitic worms that were in the water supply get caught in the collecting vessels. They basically grow there and they become trapped there, and this does not allow the free passage of lymph through the rest of the vessels. And so those worms basically live there, and it causes the fluids to become trapped in those extremities. Another issue that can arise would be compartment syndrome. Compartment syndrome points to the idea that muscles are actually necessary for milking. Now, we've discussed this previously when we discussed the venous system, the idea that when the skeletal muscles contract, they're going to allow the squeezing of vessels, veins, particularly deep veins, that are buried within them. Well, the same is true actually of the lymphatic system. The lymphatic system tends to run parallel to muscles, and it really depends on those muscles contracting and properly moving and squeezing the vessels so that the lymph is milked along the pathway. However, sometimes there can be muscle damage. So muscle damage could lead to compartment syndrome. It has a particular look to it. Again, we're talking about trapping fluid. However, this is a little bit different from elephantiasis. In elephantiasis, you're directly trapping some of those vessels. But in compartment syndrome, you literally cannot get any fluids past the muscles. As you find difficulty returning the lymph through the vessels, you trap so much fluid in the extremity, for example, in the hand, because of, say, a muscle injury in the arm, that there's difficulty at some point where the muscle continues to cause issues. There's so much fluid trapped there that the arterioles are no longer able to actually bring blood into the region. And this is quite a difficulty, because if you cannot bring blood into a region, that means that you are depriving that region of oxygen. It could lead to gangrene, and there have been situations where a person did not realize they had compartment syndrome, because most people haven't heard of it, and they ended up with an amputation because of gangrenous flesh in that extremity. Right, so let's move on to the second role of the lymphatic system, which is while this lymph is being returned eventually to the blood, you need to have the ability to actually filter it. And oftentimes this is going to involve elements of the white blood cells. And so pretty much any kind of the lymphatic system that is involved in any organs of the lymphatic system that are involved in this filtration process will have a lot of white blood cells, and they're going to oftentimes have these lymphoid follicles. Now, lymphoid follicles, it honestly kind of looks like a cell with a nucleus in the middle, but it's much larger. It actually has many cells within it, and generally speaking, it's going to have these germinal centers in the center, which usually contain huge populations of B lymphocytes. And then around the outside, it's going to appear kind of darker in a histological slice. That area there is going to have other white blood cells, such as sometimes macrophages or dendritic cells or T lymphocytes. So watch for, when you're looking at histological slices of the lymphatic system, you want to watch for these lymphoid follicles. So one example of where you would find them would be in lymph nodes. Lymph nodes are definitely the most ubiquitous organ of the lymphatic system. And so we're going to be drawing, it kind of looks like a kidney bean. It's about 1 inch in diameter. And let's draw the vessels going in and vessels going out. So we have 4 vessels that are called afferent vessels, which are going to be bringing lymph into the lymph node. And we have 2 vessels which are efferent vessels, which are going to be bringing lymph out of the lymph nodes. Remember, afferent at and efferent exit. And it's one way. Everything is one way in the lymphatic system. There's only one option here, and so we have valves in place to prevent backflow. And so yes, lymph will be coming into the afferent vessels. And I wanted to point out where you would find these. There's many, many lymph nodes in your body, but they tend to be accumulated in areas that are close to those lymphatic trunks. So areas like the axillary area, the anogenital area. There's many, many lymph nodes inside of your abdominal cavity with all of your digestive organs there and so on. I want to point out that there are more afferent vessels than efferent vessels. This is always true. And this is one of the ways that we slow down the flow of lymph as it makes its way through the lymph node, so it really circulates around everything. This is a good way to ensure that it comes into contact with cells that will do the lymph some good. Okay, I thickened up the outer wall of the lymph node, and this is the capsule, and then I drew some invaginations from the capsule. It's a nice thick structured wall to ensure that if you do experience hyperplastic nodes or you're experiencing an enlargement of the lymph nodes, that it won't burst. It's quite a tough outer shell here. And then there are invaginations of the capsule, which are called trabeculae, which sort of separates lymph nodes into little compartments, at least the cortex for sure. And so inside of these trabeculae, each of the separations there has its own little lymphoid follicle. And so the lymphoid follicle, remember, has those germinal centers with the B lymphocytes and a good population of white blood cells around it. And so we separate out and we label the cortex. The cortex is going to be the area that's sort of the outer part of the C-shaped organ, and the cortex is going to have those lymphoid follicles. And then there's going to be a medulla as well, and the medulla is going to have other white blood cells, other macrophages, other dendritic cells, other T lymphocytes present in that region. So massive numbers of white blood cells take up residence inside of this lymph node, and we ensure that the lymph spends plenty of time here and circulates around and kind of is blocked from exiting easily and is kind of trapped by those trabeculae to ensure good filtration of the lymph, to ensure that it's always going to be monitored properly by many, many different white blood cells in case there's any kind of issues inside of there. Next, we're going to start to list out lymphoid organs that are involved in this filtration process. This is not an exhaustive list, but it'll give you an idea. First of all, we have the lymph nodes, which we just discussed here. This is, again, the most numerous of the lymphoid organs. And then we have MALT, mucosa-associated lymphatic tissue. The name kind of describes exactly what it is. It's lymphatic tissue in the form, by the way, of lymphoid follicles, which are oftentimes buried in the walls of organs, like hollow organs that are basically, if they face the outside of the body or if they face a lumen where they might come into contact with stuff that might be filled with pathogens. So an example of this would be Peyer's patches, which are found in the distal small intestines and also in the appendix. The lumen of these then have this mucosa around them, this layer just packed with lymphoid follicles called Peyer's patches, which then monitor the foodstuffs at this point, which would be basically a waste product, and they'd be monitoring for pathogens and ensuring that if there was some kind of really egregious pathogenic issue, that would be immediately monitored and the immune system would mount an attack against it. So that is the purpose of MALT. The mucosa-associated lymphatic tissue is going to be lymphoid follicles buried in the mucosa, this layer very close to the lumen of some hollow organs. Next up, we have a pretty well-known structure, the tonsils. The tonsils, you have several pairs of tonsils which surround, they're basically invaginations of the mucosa. The lymphoid follicles actually make them enlarged, or they appear kind of swollen even under normal circumstances. So this is a ring of lymphatic tissue, chock full of lymphatic tissue, of lymphoid follicles. But they also have these crypts, which sometimes give us a little trouble. So crypts, which are invaginations in the tonsils themselves, little dips in the tonsils. The idea of the crypts is that they are meant to trap foodstuffs as it is swallowed, basically. You want to trap little samples of your foodstuffs in order to monitor the food as it's going down your throat and monitor it for any kind of pathogen that might be of danger. And so the lymphoid follicles in that region are for that purpose. The issue is that sometimes the crypts trap food a little bit longer than they should. For example, if the crypt was a little bit longer or a little bit larger or wider or deeper than it should be, it might actually trap the food for longer, which in turn causes an inflammation called tonsillitis. So this is one of the common ways that you can have tonsillitis, and sometimes you actually have to have a tonsillectomy or a removal of the tonsils. So let's go ahead and put on the side here some of the issues you might you might encounter with this particular role of the lymphatic system. Something like tonsillitis or an inflammation of the tonsils might result, especially if you have issues with those crypts in the tonsils. You might also have appendicitis. The specific role of the appendix is to trap away little samples of the bacterial flora in your colon, and sometimes this can, sometimes as you know, sometimes the appendix becomes inflamed and is oftentimes removed. It's not exactly a vestigial organ. It actually does have a role in the body, but oftentimes that role is not quite so important with the way that we now interact with our environment. So tonsillitis, appendicitis, inflammation of the tonsils, inflammation of the appendix, oftentimes due to their very role in the lymphatic system, which is to actually trap away some of the garbage and pathogens and such that we are encountering in our foodstuffs. And lastly, I'm going to mention the lymphoid follicles that are found in the walls of the bronchi. These are the air passages that go down to the lungs, and so there are lymphoid follicles buried in the mucosa of those as well. And this monitors, of course, the air that you're breathing in, against which we don't actually have a lot of protection, so we want to make sure that it's monitored closely. Right, let's move on to the spleen. Now the spleen is an organ that has a number of things going for it. There's red pulp inside of the spleen, which gives it its brick red color. But what we actually want to pay attention to is the white pulp. So there are very intense vascular structures inside of the spleen. There's a really heavy blood supply inside of the spleen. And around the spleen, around these arteries inside of the spleen, there is white pulp, which is an enormous population of white blood cells. Actually quite important for your survival. It used to be thought that the spleen was a vestigial organ, that you didn't really need it, and so they actually performed splenectomies on a relatively regular basis. But it turns out that it makes a difference for survival, for example, of a heart attack, or for your health when you go to a foreign country where you're not as familiar with the food and the water supply. Having a spleen and having those enormous, there's no redundancy, there's no other structures like this in the lymphatic system. Yes, there are white blood cells inside of the lymph nodes, for example, but the spleen is the only place where you have this enormous population of white blood cells that are ready to immediately be activated and enter into the blood supply through those arteries that they're adjacent to, and immediately go to an area of issue in the body and repair it. It makes actually quite a difference in terms of survival of certain conditions. So a splenectomy is a pretty serious ordeal. You want to make sure if at all possible, the surgeon would try to leave behind part of the spleen so that it would hopefully regenerate. This is very likely to happen, especially if you leave behind part of the spleen under the age of 12. It's much more successful. I guess there's two other issues that I really wanted to address here. I didn't know where to put this one in, so we'll just put it here next to the vascular system, the lymphatic vascular system. The issue here is lymphangitis, which is where you have an actual infection or inflammation of the lymphatic system itself. So the itis there, we've seen it a few times here. Itis means an inflammation of something. And generally speaking, what's supposed to happen is the lymphatic capillaries are supposed to trap infection, but sometimes they themselves might take on some level of infection, probably due to the types of bacterium usually that they are picking up. Sometimes there's a streptococcus or a staphylococcus that really interacts poorly with the lymphatic system, and the lymphatic vessels themselves become inflamed. So when you have a distal infection, for example, in your hand or in your arm, maybe a bug bite, a spider bite, something like that, and the inflammation starts to really spread, you want to watch for a red streak that starts to carry proximally and streak slowly up the arm or up the leg oftentimes, and this streak then in turn is bringing an infection along with it, and you have about 2 hours until that infection actually reaches the blood. Sometimes this is called blood poisoning, but it is not blood poison yet. It's only in the lymphatic system, and you have about 2 hours until it hits the blood, and yes, indeed, once it hits the blood, you could be putting that infection into the blood, and at that point it would be considered sepsis or septicemia. So you want to go to the hospital with a red streak as quickly as possible. So I'm just going to be throwing this right in there in the middle of everything. Let's talk about cancer diagnosis. The cancer diagnosis actually has to do something with the lymphatic system as well. So the way that we stage cancer usually is through the TNM method. T stands for tumor, N stands for node, and M stands for metastasis. So we're able to measure the size of a tumor, for example, and give it a rating of how large it is, basically. And M stands for metastasis, which is where the cancer is actually spread into the blood. This is usually considered the worst possible outcome of a cancer is when it spreads into the blood, because once it is bloodborne, once it is metastasized, it can spread anywhere into the body, and those cancerous cells could, for example, attach themselves to other organs. You might find that a person has lung cancer, but some of those cells have actually spread and attached themselves to the pancreas or to the uterus, for example, the outer, basically with the inner walls of these structures. And so the spreading of the cancer becomes so difficult to treat that this is oftentimes considered end stage or stage 4 cancer. Fortunately, there is a level between the tumor size and the metastasis, which is the lymph nodes. Before, just as true of any kind of pathogen, before anything hits the blood, it's going to be filtered through the lymph nodes first. And so we can look to the lymph nodes to see how much the cancer has already spread before it has metastasized. We can kind of rely on the fact that cancerous cells may slough off of the tumor, but they will be buried in lymph nodes prior to becoming part of the blood and metastasizing. So we grade the size of the tumors as 1 through 4. So if you had, for example, a T1 tumor, that would be a pretty small tumor, and this could vary depending on where the tumor was. Lymph nodes are graded from 1 through 3, which means basically how many of the lymph nodes have cancerous cells inside of them. And metastasis is metastasis. It's you either have it or you don't. So you have an X or a 0 or a 1. X means that they can't tell whether it's metastasized. 0 is it has not yet metastasized, and 1 means that it has. So if you have a T1, N1, M0, that means a small tumor that has spread to some of the lymph nodes, though not all of them, and not a large number of them, and has not yet metastasized.